Hi, everyone. Dr. Hammett here. You may be surprised to be watching this video instead of seeing it live, but there was a couple of people who said they were going to be gone, so I'm just going to go ahead and record this lecture ahead of time. Besides, it gives us the opportunity to talk carefully through a couple of things. So I'm just going to go ahead and record this lecture for tomorrow, March 18th, and upload it to my YouTube site. And then we'll just call it good for tomorrow's class. We actually won't have class tomorrow. You can come ask questions about your homework. I will also send out the exam. You can start working on that. But in the meantime, I'm just going to finish up this lecture that we got halfway through last time. And then you will be good to go for the take-home exam, which will be due next Monday. Again, I'll send that out tomorrow. We will not meet for class, but this lecture that I'm recording and I will send along to you is intended to finish the material on factoring rook polynomials, and you will need to know it in order to do one of the problems on the test, which I will show you one of the two problems I will choose to put on the test here at the end of the lecture. Okay, so hopefully that makes sense. I will also send along a link to a video that's kind of a help on 8.2 number 20, that problem that a lot of people have asked me about. It's a recording that I did during the COVID era, but it's not really that much different from things I would say were we to meet together tomorrow. So I'll send a recording of that along as well. Okay, so now let's jump in here and we'll take a look at the last half of this lecture on factoring rook polynomials. Now, I would remind you that we proved this beautiful formula last time. Remember, B1 through Bn, written in vector form, is a board, a Farrer's board, that's like written in a weekly increasing, that's like a weekly increasing partition, written so that the elements increase as you move, or weekly increase as you move from left to right, from B1 through Bn. Okay, and we had this strange notation, x down arrow n minus k. That was the falling factorial notation, which means you start with x and then you decrease by 1 for each factor. So it would be like x times x minus 1 times etc. And you keep going until you get a total of n minus k factors multiplied together. And we had this beautiful result due to Goldman, Yoshi, and White that said if you ever have one of these weekly increasing Farrer's boards, that the sum of rook polynomials times the falling factorial in minus k is perfectly factorizable into linear factors. And the linear factors are given by that. It's just going to be x plus the corresponding coordinate from the Farrer's board, b sub j, minus j plus 1. Those are the linear factors. We went through this example to kind of illustrate what was happening, and then we actually proved the thing. And the proof was basically a counting argument, if you will recall, where we constructed a board of a very specific type. We also said that it suffices to prove this polynomial identity for x a positive integer, because after all, these are polynomials on both the left and right-hand side. And if we can show that those two polynomials agree, even on like n plus 1 points, because the degree of both the left and right-hand side is n, if we can show that it agrees on like n plus 1 points, different points, then we will have shown that the polynomials must be the same. But in fact, we're showing that the two sides are equal on an infinitude of possible x values, namely any x that's a positive integer. That allows us to kind of prove this by making a counting argument. And the way that we did it is we actually made this board b sub x for x a positive integer, And we appended this little rectangle that was X by N on the bottom. Remember, the board B is literally this vector right here, B1 through Bn. That's why the dimension here is N. And the number of cells in this Ferris board weekly increases from left to right, which is why it looks roughly like the picture looks here. And then what we did is we simply counted the number of ways to place N rooks on this board in two ways. One of the ways was merely to move through the columns from left to right and just place a rook. Since we're going to have to place N rooks, we'll have to place one rook in each one of the columns. And as we do so, we get rid of one potential row for each column as we move along. And that's why you have nothing subtracted in this first thing, and then you have one subtracted in the second column, etc., which is exactly the right-hand side of the equation. And then we counted the number of ways to place these N rooks on this board in another way, namely by summing over K going from 0 to N, where K is the number of rooks that we place on the upper part of the board B up here. Okay. So we place K rooks on this upper part of the board. And if we do that, then we have to place N minus K things on the lower part, because after all, in the end, we're placing N. Okay, so it's a sum over those things. Well, the number of ways to place K rooks on the upper board is obviously the rook number of order K, the number of ways to place K non-attacking rooks on the board B. And then what we have to do is place N minus K rooks down here. And then we reasoned in class that what happens is if you've placed K rooks up here, it eliminates K columns from consideration here. Okay. So then what I'm going to do is go to the first available column, and I have X ways to place that. I mean, after all, no row was eliminated by the placement of rooks up here. I just know that there are K columns eliminated down here. Okay, so I go to the first one and there was X places I could put a rook, but then I start eliminating rows from consideration from this rectangle. So the next available column I go to, I have one less option, which is why I have X minus 1. And I keep going for a total of N minus K columns, which produces this final factor right here. And literally, if we reason this out, that is the right-hand side of this, sorry, it's the left-hand side of this equation, right? So X falling N minus K is exactly this product right here. We sorted that out last time. Beautiful, beautiful proof and a beautiful result. Okay, we ended there last time, and I said that I wanted to do a little bit more with this in this next lecture. So I want to do some applications. Let's do that now. Here we go. So first of all, we call a couple of boards Rook equivalent. These are Ferrer's boards. We call them Rook equivalent if all their rook numbers are the same. Okay, so the number of ways to place K rooks on B is the same as the number of ways to place K rooks on B prime. And we say that these two boards are equivalent. We write B and we put a little equivalent symbol here, B prime. If the number of ways to place K rooks on B is the same as the number of ways to place K rooks on B prime for all K equal to or greater than 0. Okay. So obviously, B equivalent to B prime means that the first rook numbers are the same. The first rook numbers are the same. Okay. But remember, the number of ways to place one rook is just the number of squares in the board. Yes, I've thought of as a Ferris board. And so that means that the size of B itself, that is the number of squares in B, has to be the same as the number of squares in B prime. All right, so for instance, the board 113, I'm telling you, is rook equivalent to the board B prime, which is the board 2, 3, like this. Okay, why? Why is that true? Well, first of all, the number of ways to place 0 rooks is obviously the same. That's just 1. The number of ways to place one rook is obviously the same. It's just 5 in each case. What about 2 rooks? Well, for 2 rooks over here, let's see, I could place a rook in either of these 2 squares. So I have 2 options for where to place a rook here, 1 rook here or here. Obviously, I can only place 1 rook in this row. So I could either put a rook here or here. And in so doing, to place a second rook, I could put the rook here or here. So I have 2 options for the first rook and 2 options for the second rook, these 2 squares right here. So 2 times 2 is 4. Okay. And then what about over here? What about placing 2 rooks here? Well, if I place a rook here, then I have 1, 2 options. Okay. And if I place a rook here, I only have 1 option. And then if I place a rook here, I only have 1 option. So overall, it's 2 plus 1 plus 1 is 4. So the number of ways to place 2 rooks in each case is 4. On the other hand, there is no way to place 3 rooks on any of these things. First, this one, obviously there's not, because I only have 3 columns. Here, once I place 1 rook here in this row, like I only have 1 column left. I'm only going to be able to place 1 more rook. Okay, so there's no way to place 3 rooks on either of these in a non-attacking way. So R0 is equal to R0 for each of these. And the R1s are the same, the R2s are the same, the R3s are the same. And obviously I can't put anything more than 3 either. So these are rook equivalent. Okay, so that's where these counts come from here. Okay, definition. Far's board, with weekly increasing partition here is increasing if the weekly part goes away. You just have strict increases in each one of these. So then it really looks like a stair-stepped type thing in some ways. Okay, it might jump up by more than 1 step for going from one of these BIs to the next, but it's kind of stair-stepping its way up. The example above, B prime, this guy right here is an increasing Far's board, but obviously this guy is not, because it goes 1, 1, right? They're the same. Okay, so B is not, but this guy is increasing. We're going to prove a beautiful theorem about board or rook equivalents of boards and increasing boards. Okay, so, and it's this one due to Fawata and Scherzenberger. Okay, says that every Far's board is rook equivalent to a unique increasing board. So every Far's board is rook equivalent to a unique increasing board. Now, we're going to prove this, but the proof is going to be basically kind of a sketch. There is some technicalities that we're going to skip over just for the sake of expediency, but I at least want to give you the idea of how it goes. So we're going to sketch it, and in the process of sketching it, we are actually going to see why it is, or how one actually constructs the board that is rook equivalent to the starting board. Okay, notice it says unique. So give me a Far's board. This is saying there exists a unique rook equivalent increasing Far's board. So that is where all the parts are strictly increasing. So obviously for this board right here, the unique increasing Far's board that this guy is equivalent to, 113, is this guy. Has to be, according to Fawata and Scherzenberger. Okay. Again, we're not going to go like through all the details, like we won't verify, justify the uniqueness and things like that, but we're going to go ahead and sketch this proof. So to do a proof sketch, we need to introduce a couple more concepts. First of all, the concept of a root vector for a Ferris board. It's given by, okay, so this thing right here, this is zeta, zeta. Okay, that's the Greek letter zeta. It's kind of tricky to write down, but that's zeta of B is given by 0 minus B1, comma 1 minus B2. The next one would be 2 minus B3. Okay, 2 minus B3. So in other words, what's always happening is you're going, whatever the index is, one less than that minus the corresponding entry of the Ferris board itself. So the last one in this root vector would be n minus 1 minus bn. So this guy has n coordinates in it, n coordinates, n coordinates. So the root vector is this. We'll talk about why it's called the root vector here really soon. So notice that this root vector, zeta of B, is really just 0, 1, etc. in through n minus 1, and it's like you've subtracted B1, B2 all the way through Bn. Thinking of these guys as basically like vectors. These points you're thinking of as vectors, and so you're essentially doing like coordinate-wise subtraction in so doing. Okay, so that's the root vector of a board. So here's an example. 1, 1, 3. That's our old friend. The root vector of this guy is 0. You go 0, 1, 2 minus 1, 1, 3. 0 minus 1 is negative 1. 1 minus 1 is 0. 2 minus 3 is negative 1. So there's the root vector. Okay. Now, my observation here, it's not really rocket science, is that under the theorem of Goldman, Yoshi, and White, the root vector is the vector of the zeros of this thing, because after all, this thing factored completely into linear factors. You think about it, okay? So let me just go back there real quick. I put a little breadcrumb here for us to go back to the formula. Look, what are the roots of this thing? Well, it's the negative, the roots of this, the roots of this are the roots of the linear factors. And so it's going to be the negative of this guy. Well, the negative of this guy is j minus 1 minus b sub j. J minus 1 minus b sub j, which, after all, is exactly what you have here, right? You have basically j minus 1 minus b sub j in each one of these coordinates. So indeed, this root vector is aptly named because it is the vector of roots of this polynomial. Okay? So if I have a Ferris board and another Ferris board, okay, then B is Rook equivalent to B prime if and only if the root vector of B is simply a rearrangement of the root vector of B prime. That's because, look, if these two Ferris boards, have the same root vector, then that product on the right-hand side of that equation is going to look the same. And therefore, it's going to equal this sum. And therefore, the rook numbers will be the same. The coefficients, if I were to multiply out those things, will be the same. But those coefficients of the following factorials are just the rook numbers. So that would imply that the rook numbers are the same. So don't you see? If the root vectors are the same, then the right-hand side of the Goldman-Yoshi equation is going to be the same, which means if I were to write it in kind of a funny way with these following factorials, I would have the same rook numbers showing up. Has to be the case. Okay? Has to be the case. So rook equivalents is the same as root vectors being a rearrangement of each other. Okay. And I would just notice that we had this right here as our root vector. Let me go back here and just point out, like, those were literally the roots. So like -1, 0, and 1, those were the roots of the right-hand side, weren't they? Right? Which is exactly what we have here. I mean, I thought I would at least just point that out. Okay. So B prime equals 0, 2, 3. That was Rook equivalent to B, wasn't it? We just saw that on the previous slide. And the root vector of B prime, of course, I get by going 0, 1, 2, minus, okay, 0, 2, 3, okay? Yeah, I'll explain in a minute why. Well, okay, so 0 through the, so I mean, I'm trying to make it so that these boards have the same number of coordinates, just to kind of compare the two, right? So I padded a 0 on the front of this, and you'll see later on why it is that we end up doing that. But anyways, so 0, 1, 2 minus 0, 2, 3, of course, I just end up with 0, right? Because 0 minus 0 is 0, 1 minus 2 is -1, 2 minus 3 is -1. So notice that that's just a rearrangement of this thing up here. So there you go, right? I want it to have the same number of coordinates, so that the degrees of the corresponding Rook polynomials are the same. Okay, I hope that makes sense. Okay, so that's pretty cool. So this is another way to show that the boards are board equivalent without having to compute the Rook numbers. You just look at the root vectors, make sure they have the same number of coordinates, okay? But then look at the root vectors, and if they're rearrangements of each other, then the right-hand side of these things are the same. So therefore the left-hand sides are the same under Goldman, Yoshi, and White. And so the boards are board equivalent, Rook equivalent. Beautiful. So then you know the Rook numbers are the same. What an amazing thing, for sure. So every Ferrers board is Rook equivalent to a unique increasing board. That's the theorem of Fawata and Scherzenberger. Let's do a proof sketch. Like I said, it's going to be a proof sketch. So the first thing that we're going to do is pad the board B that you start with, which isn't necessarily an increasing board, with enough zeros so that the root vector of B, and by the way, it's annoying to have to keep writing root vector of B, so I'm going to call that just zeta for short, okay, for this board right here. I pad it with enough zeros so that when I compute the root vector, the thing starts with a 0 and has all entries that are positive. I mean, that's going to be possible by just slapping enough zeros on the front of B. You can kind of try that with some examples. But after all, the way you compute the root vector is by going 0, 1, 2, all the way up through n-1. Notice this thing has n total entries in it. If I slap on enough zeros, this stair step, this perfect stair step thing is going to be such that it overwhelms the entries of the board itself, padded with a bunch of zeros. And so I can make all of them positive. So I want to pad it with enough zeros so the thing starts with a 0 and has all entries that are equal to or greater than 0. So it's like I avoid this business right here. I slap enough zeros on so that I have no negative entries when I compute the root vector. Now I will say that we will do this example later on, so you'll see the sort of thing that we're doing here. But this is it. This is possible to do. Denote the maximum of this root vector by m. And it turns out that you're going to have somewhere, if you think about this very carefully, if you pad it with enough zeros so that this kind of thing is happening, the maximum entry, you can actually walk up to it one at a time, right? So there's going to be entries in the root vector that are from m down to 0, like just, there's going to be an m somewhere, an m-1 somewhere, an m-2, down to a 2, 1, 0. Okay, and then you have some other entries as well. So we rearrange this root vector. Remember, m is the maximum of these things. Rearrange it so that all of those things that are consecutive up to m are at the front. So it's like 0, 1, 2, all the way up through m. And then these guys here are going to be in decreasing order. Okay, it's weakly decreasing order. So I just shuffled these things around in the root vector. Remember, this is the root vector. I've shuffled them around so that you have this stair step going up to m, and then these guys go down. So it kind of goes whoop up and then down, right? But these are weakly increasing. Okay. My claim is there exists an increasing board B prime with root vector of B prime equal to zeta prime. Okay, there exists an increasing board B prime with root vector of B prime equal to this thing right here. This thing right here. Indeed, it's because this thing equals, let me just kind of write on here, that thing equals, 0, 1, n minus 1. So let's see, how many total entries are there here? N plus 1, is that right? Are there n plus 1 entries here? I think that's right. I think there are n plus 1 entries. Okay, so this zeta prime is 0, 1, 2, just so it's clear what's going on here, all the way up through n minus b prime. Okay, and so you're going to be able to solve for b prime. You can figure out what the parts of b prime actually are, right? B prime is simply going to be 0, 1, 2, n minus zeta prime. Okay, zeta prime. And the thing is, like, the first entry is going to be 0, but that's okay. And then you figure out what your board actually is. It's a beautiful thing. I'll leave it to you to kind of think about why it is that these things increase perfectly the way that they do up to m. But other than that, it's pretty clear you can kind of get a b prime from there. Why is b prime increasing? You could think about that as well. Why is b prime unique? Well, you could think about that as well, but it is for sure. That's why I said this was a proof sketch. There's some things that are a little bit technical that we're not really checking fully in this case. But at least this gives you a way to construct the board B prime. Okay, so let's do an example here. First of all, we go back to our old friend B, which is 0, 1, 1, 3. Or actually it was 1, 1, 3. But remember, the first step was to pad this thing with enough zeros so that all of the root vector entries will be positive. Well, I'm gonna have to slap on at least one additional 0, because before we got negative ones, right? So we padded this thing with a 0 right here. Okay, you pad that thing with a 0 so that when you go 0, 1, 2, 3 minus that, you don't end up with negative things, right? So like 0 minus 0 is 0. 1 minus 0 is 0, 2 minus 1 is 1, and 3 minus 3 is 0. So all the things are equal to or greater than 0, which is what you wanted to do. Okay, what is the maximum of all these entries? Well, it's 1. It's 1, okay? It's 1 in this case. And then it says to rearrange it so that there's a perfect stair-step increase starting from 0 up to that maximum entry. Well, that means we're going to have to shift some things just slightly in here, okay? So like this. So that means zeta prime is 0, 1, and then 0, 0, right? So like zeta m plus 1 prime and then zeta n prime in this case are just 0 and 0 respectively. M was 1. So 0, 1, 0, 0, that's zeta prime. So B prime, remember what we did? B prime is gotten at by simply taking 0, 1, 2, 3 and subtracting zeta prime. And if you do that, look what you get. You get, right, the ones cancel each other to give 0. Of course, the 0 minus 0 is 0. But then 2 minus 0 is 2. And then 3 minus 0 is 3. So look what you get. The board is 2, 3. And like, you know, you ignore these leading zeros, of course. The real board is sitting right here. But we get our B prime, which we knew we had to do. We had already checked that this thing is board equivalent and that it's an increasing board. So we have this constructive way of getting this thing. How cool is that? Okay, so we get our board 2, 3 right there. Okay, I think what I'm going to do is I am going to go do another example somewhere else that's maybe a little bit more in depth. Okay, so here I am. Let's do a little example here, a little bit of an example. Okay, so I want to look at this kind of special board. Remember, we had that board 113. I'm going to call that L3. So L3 is the board 113. Okay, so like for example, you know, L2, how would I define L2? It's literally like an L, like 113, you know, was this. Okay, the third one was this. So basically what you do is you kind of, the third one, you copy what you already had in a row as kind of a column on top of that last entry. So like L2 would be 1, 2. Do you see what I'm saying? Because it would be like this and then like this. Okay, so the whole point here is there's 2 here and there's 3 here, and you just start with a bunch of 1. So like L4 is going to be 1, 1, 1, 4, right? So you basically have n minus 1, right? So there's 4 minus 1, 4 minus 1, 4 minus 1, oops. Okay, let me do this. There we go. 4 minus 1 ones, and then the nth entry, the fourth entry is 4. So in general, Ln in this example is going to be, you know, n minus 1. Right, so there's going to be n minus 1 ones, and then this. Okay. Okay, so this is n right here. So L1 is going to be 1, 1, right, 1. There's a total of n minus 1 of these, and then there's an n. So notice that this guy is a partition of, right, a weekly, okay, and we've written this thing, it's a weekly increasing thing. It's a partition of n plus n minus 1, which is 2n minus 1. There we go. Okay, so you might ask yourself, well, what is the board equivalent thing that, or what is the thing that this is Rook equivalent to? What is the board that this thing is Rook equivalent to? So what's the L prime that is increasing such that Ln is Rook equivalent to L prime? Okay, guaranteed by the Fawata-Scherzenberger theorem. Okay, so what is it? Well, we already did it in the case of L3, right? We figured out it was the board 2, 3, correct? So what do? Well, we compute the root vector of Ln. And remember, we have to pad this thing with enough zeros so that when we compute it, we end up with things that are with differences in each coordinate that are all non-negative, like 0 or above. So, it's going to be 0, 1. And so because Ln originally started with a 1, and I don't want to go 0 minus 1 and get something negative, I have to pad a 0 on there. But then I'm good to go after that. Okay, so it's going to be 0, 1, 2, ... Let's see. I'm just going to add 1, 0, which means now I will have n plus 1 positions. Okay, so this is a total of n plus 1 positions, and I subtract Ln from this thing, which is 0, 1, 2, ... and minus, and I pad it with some zeros. So it's going to be 0, 1, ... 1. Okay, the ... is probably unclear, but I have n minus 1 ones. And then in the last position, I have an n, right? So there's a total of n plus 1 things here. Okay, if I do this, what do I get? Okay, so zeta of Ln is equal to, well, 0 minus 0. 0 minus 0 in the first coordinate is 0. Okay. 1 minus 1 in the second coordinate is 0. 2 minus 1 in the third coordinate is 1. 3 minus 1 in the fourth coordinate is 2, etc. Okay, so etc. When does this stuff stop? Okay, so let's see here. So 0, 1, 1, 1, 1, 1 through n. What do we get? So 0, 0, 1, 2, all the way up through, let's see here, it's going to be n minus 1 minus 1, because there's right here in the position right before it's n minus 1, and I subtract 1 to get n minus 2. And then n minus n is 0. See what I'm saying? Okay. So, I mean, just keeping track at home here, this is n minus 2, and then there's 1, 2, 3 more entries. N minus 2 plus 3 is n plus 1 entries total, which is exactly what we should have. And then remember, zeta prime we get by rearranging entries to start with a single 0 and work all the way up to the maximum. And in this particular case, what is the maximum? Okay, well, the maximum is this. This guy is our m. That's the maximum. Yes? So let's see here. What do we get? Well, zeta prime is going to be 0, 1, 2, all the way up through m. what is m? M is n minus 2. And then how many entries are left? Well, I already used 1 0, and now there's just 2 more zeros at the end here. Okay. And then how do we get our L prime? Well, L prime was gotten at by actually taking the stair step thing, as many coordinates as I need, n, and then we subtract zeta prime. And so what do we get? L prime is equal to, let's see here, L prime is going to be, all right, well, zeta prime, you end up getting a bunch of zeros. How many zeros are there going to be? Well, right, it's going to exactly be like the stair step thing until I hit the entry that equals n minus 2. Okay, so there's n minus 2 plus 1 or n minus 1 total entries where that happens. Okay, and then the last 2 entries are going to be the only ones that aren't 0. Last 2 entries. So remember, this guy right here was gotten at by doing n minus 2 minus n minus 2. But then the last 2 entries, which are n minus 1 and n, I would be subtracting these zeros right here. So it's going to be n minus 1 and then n. Okay, which when you think about it is just this. Okay, so boom, boom, boom. Okay. With one guy like this. So on this side, there are n minus 1 things. And on this side, there are n things, right? Because the zeros we just kind of ignore. And that exactly comports with what we learned before. Because remember, before we had learned that like L3, for instance, right? L3 is Rook equivalent to 2, 3, right? So L3 was 1, 1, 3. 1, 1, 3. Or that thing was Rook equivalent to L prime, which was 2, 3. And here that's saying exactly that. It would be 0, 2, 3. Yeah, which comports with what we already knew. Can we see something else that would be interesting? Well, I don't know. Let's see. Like what would L15 be Rook equivalent to? So L15, what would L15 be equivalent to? Well, it would be equivalent to, so that's the one where you have literally 15 or like 14 ones. Okay, so 14 ones. There are 14 of these, 14 of these. And then you have a 15 in the 15th position. Okay, or sorry, that's not even Rook equivalent. That's just straight up equal. Okay, but what is this Rook equivalent to according to this? Well, according to this, what you do is you take those 14 things right there and you just stack them up right next to the 15. Okay, so this thing is Rook equivalent to 14, comma 15. Okay, that would be that's the L prime given by the Fawata-Scherzenberger theorem. Okay, so this is the increasing board that is Rook equivalent to this literal L shape that we've extended from our ongoing examples. All right, I think that's pretty slick. So we've seen how this thing is illustrated. A couple more things here. I said that on the test I was going to give you a couple of one of 2 problems to think through. Okay, I just did the extension of this thing right here, 1, 1, 3. We did 1, 1, 1, 1, 1, 1 for n minus 1 ones, and then in a stack of size n. We figured out what that thing is Rook equivalent to under Fawata-Scherzenberger, the construction given here in their proof. But here's a couple of exercises. One is, remember Bn? Bn is just the box, the n by n box, the n by n box. It's the Ferris board. So one potential problem would be for me to ask you what the Rook numbers are for any k. All right, we actually already talked about that in class, but it's free points. Factor this. Okay, well, you should know a way to factor it based on what we've just been talking about for 2 lectures. You know, something goes over here. Okay. See, find the unique increasing board that's equivalent to Bn. Okay. So Fawata-Scherzenberger, right? So like, here's a hint. B and C you should be able to use the theorems that we learned. Okay. 2 is a different one. So there, look here, I just wanted to kind of look at that stair step thing, the stair step thing itself. This is an interesting one right here. RK of Tn, so the root number of ways to place k non-attacking rooks equals the set of the number of set partitions. A set partition is a disjoint, a non-trivial disjoint way of writing the set as a union. Okay, so it's a number of ways to do that. It's number, okay, so like show that the number of ways to place k non-attacking rooks on this board is simply the number of set partitions of 1 through n into n minus k subsets. Okay, n minus k subsets, specifically n minus k. That's related to something called the Stirling numbers of the second kind, which is an important concept in combinatorics. Of course, it implies there's something called the Stirling numbers of the first kind, and there are. Factoring this, again, maybe there's something in the last 2 lectures that would help. Give another proof of the factorization identity in B, maybe by thinking about the proof of the other guy, which, by the way, on the test, you can go back and read through the slides. That's allowed. Give a second proof of the identity by counting the number of functions from the set 1 to n to the set 1 to x, where x is a positive integer, in 2 ways. Okay. Maybe by looking at the left hand and the right hand side of this thing, the sum version and the product version. Okay. And then find the Fawata-Scherzenberger increasing board that's board equivalent to this. I'm not going to say anything, but hello, something's clearly true here. Okay, I'm going to leave it at that. Like I said, I will put up this video. I will put up a link to a video of me talking through 8.2 number 20, which seems to be causing a little bit of trouble for a couple of you. But we will not meet tomorrow. I will send out the test tomorrow. That's all I have to say for now. Enjoy the weekend, and please do reach out if questions should arise. See you guys later.